Good afternoon. We had talked about having our session on Thursday evening at 5, right? Unfortunately, that directly conflicts with the senior thesis poster presentations. So we can either try to go earlier or later or pick a different day. Tonight's not a good one. Not tonight. I assume you would need more time. Fair enough. So, what's that?
We do it later.
Like after the poster?
Like after 5 o'clock.
Sure.
It's at 6.
What time is the poster? I thought we did too.
5 to 7.
I said 5 and you were like, no.
Oh, I don't care. 7 work? 7 works?
Sure. You can do it.
I can pretty much do any time except tonight.
Get something going on tonight?
Yes. So 7, right?
Sure.
7 p.m.
Oh, that's not.
So you're just thinking that's it. It's 5
So we say 7, right? If you get here early, I don't have to buy you pizza.
Wait, if you
They have food at the senior poster thing.
Did we also talk about the final? Because I received the email that we said it was the wrong day for Tuesday.
Yes, so the time that I wrote on the syllabus apparently is incorrect. And let's see. I think that I can pull that up here. I don't care when you take the final, I mean, obviously, but you might. Let's see, do I have internet?
Yeah, that's like our thing.
Much better. No?
So, but we can still be here.
You don't get a reading day this semester, which is kind of odd. Have you had a reading day before?
What do you mean a reading day?
Day when there are no exams. So you probably can't see this. Let's see if you can.
I can kind of see it.
All right, so we are 11:20, which puts us here, right? And if we
No, that's one. Oh.
1:20 Monday and Wednesday, right? And so the issue we have is, I think what it was set for before, it said Thursday, which maybe was
Wait, said Tuesday before.
said Tuesday before. So this class used to be at 12:20 is the problem, and apparently I forgot. So we're at 1:20, which puts us at Wednesday at 1:15. Does that work for everybody?
So we're Wednesday.
So you're Wednesday at 1:15.
Cool. So
Now,
I
yes.
would have 4 exams that day.
Why?
Well, so because I would have optics.
No, I don't even know what they are.
Yeah, just
So I'm willing to offer the exam at another time, but my thoughts are that I'm out Sunday and Monday. I get back late Monday. So that's not a good day for us to try to do a review because I can't tell you what time I'll be back. And so it means we could do it Tuesday or we could do it Wednesday. And that's going to dictate when you take the exam potentially, if you want a review.
I haven't started organizing.
Are we not reviewing Fridays?
Well, we can, but that was when I thought the exam was on Tuesday. There was no time to do a review before that. So we do the review on Friday. What time was that scheduled for?
Like in class is when we
Oh,
had
in
planned
class.
for it, yeah.
Okay, fine with me. So we'll stick with that. So as far as I'm concerned, in terms of when you take the exam, I don't want to set more than 2 times for the exam. In other words, one will be the normal exam time. If you wish a different time, you need to come up with a consensus on what that would be because it's not fair for me to have whoever's going to proctor your exam have to be here multiple times for that. In other words, I'm not doing it. Yes.
Is Monday off the table for the exam?
Not for me, I don't care.
I'm not.
I see no reason for me to be here during your exam. Clearly.
We already have to
Right.
Monday.
Can we do it Tuesday? Because I might be wrong, but I think that thermal analysis is also on Wednesday, and the last final is also on
Yes.
It is on Wednesday. It's at 3:30. Thermoanalysis.
Yeah. So then this test would be before, and then the last would be before.
Oh,
Can we take this test on Tuesday?
Sure, I'm fine with that. We can keep the time we scheduled. We already had written in for Tuesday.
Yeah.
We'll just keep that time then. Are you good with that?
So, is it Tuesday and Wednesday, or?
It's Tuesday or Wednesday, not Tuesday and Wednesday.
Well,
You don't get to
okay,
take
sure.
it twice.
Well, we're not doing it twice, but like, yes,
Tuesday or Wednesday.
yes. That's
Grammar
what I
is
meant to
important.
say.
I know some of you would take it twice. Not that it would help you, but you would take it twice. All right, so we're good for that? So there are 2 times, right? Tuesday, 1:30, right? 1:15. Wednesday. The PM's important. Okay, and then last, your project presentations. Seven PM Thursday, tomorrow. Correct? Okay, and review sessions in class on Friday. Exam is comprehensive, covers the whole semester. Okay? Good. So, we wrapped up drying, didn't we?
Yes.
We went through all of this, 2 approaches, blah, blah, blah. Micromechanical and macromechanical stresses in the system. We got to about here, I suppose, didn't we? Better? I mean, I know you've had a week and a half off, but come on, all right? Constant rate period, okay? When it's corrected for shrinkage because you're losing surface area of the piece with shrinkage, right? When you get to the point where the water is receded into the pore structure, you no longer have any more shrinkage, okay? So your opportunity for damage occurs in the system basically at this point. At the end of shrinkage is the last chance you have for damage in the system. Now that's generally true when you have water left in the pores, but there's no more shrinkage, there's no more rearrangement. In the absence of rearrangement, right, there's no strain in the system ideally. That doesn't mean you can't blow the part up potentially if you were to heat it excessively high, right, so that you can generate steam, but we don't consider that to be reasonable. Then you get the first falling rate period, which is here, and then the second falling rate period is elimination of the water and the meniscus between the particles. Right, that's your most difficult to remove and takes the longest time. Okay, ideally. Okay, so this is critical moisture content, and then this is your end of shrinkage, and they're pretty much at the same place. So you're going from the pores being filled with water and particle rearrangement, which can be significant in the drying process, to a body in which you have only small amounts of water left in the system, and that amount of water basically is just holding the particles together more or less, and then it's being removed in the last stages through evaporation and then diffusion out through the pore structure. Everybody likes to look at this different ways. They draw it different ways. We don't really care so much about that. This is probably the best chart for you to recognize. okay? Because it is very simple in its explanation of what's going on, and it shows you very clearly what's happening in terms of evaporation. So why do we have a constant evaporation rate? Okay. What does that tell you? We've discussed it in the context of evaporation from a free surface, right? So if you set a pan of water out and you monitor the rate at which water evaporates from the surface, you get more or less the same result. And what that tells you is that the body actually then approximates what would be called a wet bulb. Did we talk about that in here, measuring humidity? Some of you are saying yes, and some of you are saying no, so I'll take that as maybe. You may have done this experiment in grade school, actually, where you went to school. So you have a thermometer, the second thermometer, okay? One of them is in a more or less like a sock, okay? You have water here, a reservoir of water, wicks water up, and then water evaporates off the surface, okay? And this is called a wet bulb. This is called a dry bulb. You have a temperature here, you have a temperature here, and the difference in temperature is due to evaporative cooling. Okay, so as you evaporate water from the surface, evaporation of water is a strongly endothermic process. It requires a lot of energy to evaporate water. And so if you have a wet surface, the temperature of that surface is cooler. And that difference in temperature between dry bulb and wet bulb is dictated by the humidity in the air. So you can argue it's also dictated by temperature, but humidity. So if you have low humidity, then your evaporation rate of water from that surface is fast. If you have high humidity, then the evaporation of water from that surface is slow. So your delta T is directly related to humidity, okay? So if your delta T is greater, your humidity level is lower, so you can say it's inversely related. Okay, so delta T is dictated then by the difference in temperature between wet bulb and dry bulb. So there's a device that's set up, that's why I said you might have seen it before. It's simply a device that allows you to spin the thermometer, but you have to have water on the wet side. Otherwise the temperatures are the same. In other words, blowing on a thermometer doesn't change the temperature. Right? It only changes the temperature if you have water evaporating from the surface of that thermometer. So in your car, for example, you have a temperature indicator. Where's the sensor go? Where's the temperature sensor in your car? Does it make a difference if it's in the wind? No, right? Unless it's wet. You see what I mean? You don't care where you put it. You just want to put it near the engine, or else the engine heats it up. It's always the same temperature. Bad. Right? So that temperature doesn't. It tells you the dry bulb temperature. It tells you nothing about humidity. It tells you nothing about how fast you drive. When you drive faster, temperature doesn't go down in your car. Well, assuming constant temperature outside, right? So, if you evaporate water from the surface, then it cools the wet bulb. You have that delta T. So the evaporation of water from a free surface is essentially that evaporation. So the ceramic body, this is essentially your ceramic body, drying ceramic body. Okay, so that's your wet bulb. So if you have then a way to measure humidity, which you can do by this method. Now there's other ways of doing it. Okay, that's probably the most easy to understand. And so then what you get is if you look at the temperature and the humidity level, and you know what the temperature is of the air going in or whatever, you can calculate then the relative humidity in the dryer. You can also calculate the temperature of the body. Okay. So, I don't care about that. Well, this shows us that this is for brick shale. It doesn't make a difference. We like to categorize ceramics into different things and act like they're different, but they're not. Okay? Evaporation of water from a traditional ceramic body or an advanced ceramic body, there's no difference. It's still evaporation of water. This just shows you that if you go in here and you look at the dash line, that's saying your dry air at 80 degrees C. So it's hot, dry air. 80 degrees C is very hot, dry air. Okay? And you see that you'll hit end of shrinkage at a much shorter time frame, but also at a little bit lower moisture content. And part of that has to do with how fast you're evaporating water from the system and you get a lower shrinkage value in general. That's here. Oh, sorry, yeah. This is your shrinkage value. And then if I dry slower, I get more shrinkage. So what happens is the outside dries, and the inside remains sort of the jelly center thing, and you don't get as much shrinkage out of the system. If you slow that drying process down, so the solid lines are 50% relative humidity at 50 degrees C. That's still hot, okay, but you have more humidity in the air. That slows down the evaporation rate, and you get more uniform shrinkage. And the argument that has brought up all the time is that if you dry too fast, the body cracks. Correct? Also, lots of arguments for warping, which is possible, but that's very rare for us to see that. Only in very specific conditions do you see that. So what do we argue for warping and cracking now?
Subjects,
Say?
defensive gradients.
Yeah, it's a forming problem. It's not a drying problem, not a sintering problem. It just shows up there. Okay? Now, when I say it's not a problem, but it shows up there, you can say, well, doesn't that make it a drying problem? Well, my point is this. I get cracking in the body on drying. If I dry it slower, the argument is, oh, I'll avoid the cracking. But my argument would be that's not true. It's not the evaporation rate of water from the surface. It's the ability of particles to rearrange and compensate for density gradients. If you're unable to do that, it doesn't make a difference how fast or slow you dry it, then you get cracking because you have large density gradients. And otherwise, you can get those density gradients are smaller. You'll see them in sintering where you get greater shrinkage amounts. Okay, so we would argue that it's not the evaporation rate or the drying phenomena that controls that behavior, that is your forming process. So we have a disconnect, right? If you go into literature, there is a lot of literature that has to do with drying. Why is that if it's not the cause of drying? If drying is not the cause of cracking? Because that's where the cracks show up, and then everybody gets bent out of shape about that and decides, wow, we need to pay attention to the dryer, okay? But I will tell you from interaction with factories, things are going along just fine, okay? And then everything starts to crack, and the immediate response is to go adjust the conditions in the dryer. But my take is that nothing else has changed. Weather front moves through, changes humidity. Well, that could affect it because you have incoming air. Change in barometric pressure, not sure how that would affect it. Small change in the ability to evaporate moisture. Changes in temperature, no, I'm heating the air, so it doesn't make any difference. You know, there was a change in the process someplace up the line, upstream, okay, that caused the problem. So we have this chart that shows us about psychrometric chart, and I'm not going to go into a lot of detail, but I can give you a copy of one, okay. Psychrometric charts are ways to predict temperature and humidity. What's the biggest use of these? Do you know? Yeah, heating and air conditioning. Okay, so if you live, let's say you're fortunate enough to live in Texas, in Houston, where it's 97% humidity, right? Now you're talking about having to change the temperature of the air, and the air is laden with moisture, so the amount of energy required to change temperature goes way up because you are talking about how to remove moisture from the air or how to change the temperature of the air that's containing a lot of moisture. Whereas if you live, say, in Minnesota, okay, where the humidity is low, okay, then the amount of energy necessary to change temperature is dramatically reduced. So these charts are designed actually to predict then the amount of energy required to change temperature. And they do that here with enthalpy, which are these lines that move across in this fashion, okay, and they are kilojoules per kilogram of dry air. First piece is right here. This is the x-axis, this is the dry bulb temperature. So you have 0, someplace in here is 10, here's 10, 20, 30, 40, 50 degrees C, okay? And then this curve here is the wet bulb temperature or the saturation temperature. So this curve is actually the 100% saturation level. So you'll see that 10 relates to 10, or 20 here is 20 there. So that means that your wet bulb and your dry bulb are the same temperature. And they are the same temperature because there's no room for evaporation. There's no room in the air to handle moisture. So you know the great joke about moving to Arizona where it's a dry heat. Yeah, it's still hot, right? But then when you sweat, evaporation rates are very high. That creates a cooling effect. Okay. In places where you have warm, it's very, very warm, people were quite clever and generated water vessels that were slightly porous actually porous. Okay, water goes to the outside and evaporates, and it actually cools the jug. It's actually quite clever. So what we have here is a series of lines. Okay, this is 100%. Here's 90, 80, 70, 60, 50, and you can't really see that. I get that. Okay, and then you have lines here like this. So if you were at, say, 20 degrees C, and then your wet bulb is 15, you come down to where it hits 20. That's a bit far. Wrong line. The right line here. Here they are, the dash lines. Okay, you come across to here where you hit 20. This tells you you're 40% humidity. So if your wet bulb temperature is 15, okay, and your dry bulb temperature is 20, okay, here where they intersect tells you your relative humidity, which is 60%. Okay, so that's called a relative humidity. The reason it's relative because it's not a constant, and it changes with your dry bulb temperature. Okay, if you go up in temperature, then the temperature of your wet bulb will scale, but not linearly. It's a nonlinear function because you're talking about evaporation. The last thing on this chart, this doesn't show up very well here, but horizontal lines that tell you the absolute amount of water. So a general rule of thumb is at standard temperature and pressure in general, at 50% relative humidity, you have 1% water in the air. Okay, that's a lot of water. What is the volume of 1 mole of water at standard temperature and pressure? What a great question. 22.4 liters, right? That's the volume of 1 mole of any gas at standard temperature and pressure. Correct? So you can calculate then what the volume would be for that amount of water. Okay, and that's a lot of volume. What is the mass of 1 mole of water? This is not a trick question. 18 grams per mole, right? So you go from 18 grams per mole, which is by volume, not gas. 18 grams of water is 1 mole. What's the volume of 18 grams of water? 18 cubic centimeters, right? So look at it that way. 18 cubic centimeters goes to 22.4 liters, right? Which is 22,400 liters, cubic centimeters, right? So this is an increase in volume of approximately, about 1,000. Okay, so the volume of water expands by a factor of 1,000 when it goes from liquid to gas. Okay, that's why steam is so efficient as a power source, right? Because a small amount of water expands into a huge volume, and that expansion then you do things like move pistons and what have you. Okay. So this is the macro-mechanical view of drying. If you were to look at this chart, this little insert here is important. I thought I had it as a slide. I don't seem to see it here. Wonder why not. Let's do this. Okay, this shows you that if you were to take this wet bulb, dry bulb thing and leave it stagnant, okay, what you find is that the humidity would seem to be different if you move air around it, okay? And the reason for that is that in slow-moving air, your humidity would appear to be at the same distance from the bulb, the humidity would appear to be greater, okay? And that means that the difference in temperature between the wet and the dry bulb are closer together, right? So they're closer together, your humidity is reduced, okay? And the reason is that on the surface of the free surface, okay, So you have a saturated body. You build up a stagnant layer on that surface, okay? And that stagnant layer then slows down the rate at which water converts to, basically gets evaporated. So it's a slow move through here and then faster when it gets out of there. But that slows down, you have a boundary layer effect, what's called. If you blow air over the system, it removes that boundary layer, and then your evaporation rate can improve. So this is the equivalent of blowing on your food. Okay, so the impression is, right, that if you blow on something hot, it gets cooler, but recognize that most of the time what you have is water in the food, and that's what's actually happening is you're increasing the evaporation rate, and then that tends to cool the system more quickly. Okay, so what we do here is that I told you that you swing this thing around. What you're doing is you're increasing the velocity by the wet bulb so you get a more accurate measurement of relative humidity because that boundary layer slows down evaporation rate and gives the appearance of a greater level of humidity. And you can argue that actually in that boundary layer your humidity level is greater. Okay, so it slows down evaporation rate. Yes?
In a totally dry system, wouldn't flowing air over it still cool it faster?
No.
But wouldn't you be replacing like heated air at the surface with essentially cool air and cooler air? Or is it just air is such a good insulator that it doesn't matter?
Air is a remarkably good insulator. So typically, the reason you feel a reduction in temperature is because of evaporation. Okay? So, so if you're going to dry a gypsum mold, for example, what's your limitation? Do you remember this discussion? What happens to plaster of Paris? You mix it with water farms gypsum, right? And then you have water saturated pores. What's the problem? No. What's the problem? What are you going to do? You going to throw it in the dryer? Why not?
So you change the structure, it won't be gypsum anymore.
Right. So at 96 degrees C, okay, gypsum goes to anhydrite. Change in crystal structure, change in density, sample cracks. Okay? So, how do you dry it? You don't need heat. You just need a fan. Okay, so put a fan in front of the gypsum mold. It will dry very quickly. You know, it will maybe take an hour or two, but it will dry quickly. No damage to the mold. Okay, so what you're doing is you remove that surface stagnant layer. Evaporation rates go way up. You'll dry the mold very efficiently. Okay, so. George Scherer developed this model. This is the micromechanical model. He developed this network. It's soon to flatten meniscus when you start, and as soon as you cool that, start to evaporate water, you get a curvature of that meniscus, radius of curvature, and then he calculates a bunch of stresses associated with it. And then the argument is that, oh, well, I have this constant rate period on the left, okay, and the idea is I'm shrinking the body, but my evaporation rate stays the same, okay, and then in the next step, he says, well, starts to move into the body, but typically this network will get shrunk, okay? And that shrinkage process, we don't have this network per se. We have a bunch of particles forming this network. So this cartoon version doesn't do very well for us because we start thinking of this as having pore channels, but what you actually have is a bunch of particles, basically space in between them, and you can argue for pore channels, but they're not well defined. They are essentially this tortuous path of water through a pore system. Okay. Now he was really interested in drying of gels, and gels represent for us a rather specific special problem because you have extremely high surface area particles and you have a lot of water in the system, and that requires a huge amount of rearrangement of particles. And if you do that in such a manner that's done too quickly, those particles do not have time to rearrange. The other thing that we have found is that by increasing the ionic strength, those particles will coagulate at the secondary minimum, and then they're able to rearrange each other more easily. Now that's going to suggest that you can create damage in drying. Fair enough, you can, okay? But if you increase ionic strength, then in fact your drying stresses are dramatically reduced. Particles are able to rearrange more efficiently. So the system is locked up and unable to rearrange. That can create some problems for us, okay? So having salt in the water of some form or other, some ionic strength in the water, is beneficial to drying. We don't have direct data, we have anecdotal data, meaning that we see that the strength of systems containing higher levels of salt after drying are typically greater than the strength of systems which do not have that salt. Okay? It is an argument for the use of tap water in ceramic processing, and it certainly is a good argument for traditional ceramics. It's not such a good argument where you have advanced ceramics that are sensitive to small changes in chemistry. Okay? George then predicts that you will get cracking based on stresses in the system, okay? And meniscus forces are such that this curvature that you have and the evaporation rate is enhanced by that more gentle curvature compared to here. So then you evaporate water more on this condition that gives you greater compressive stresses that cause then tension in the system and eventually cracking. Okay, your greater tension in the small pores, is what it's doing is it's pulling this material away from here, and that's creating a crack in this crack in this direction. You should recognize in ceramics that we always fail in tension, right? So that means your stresses are going to be perpendicular to this crack direction. It is in the direction of that smaller pore. What's the problem? Well, it implies that I'm always going to get some sort of cracking in the drying of a ceramic body, and that's not what we typically see. Okay? The other thing is that this would imply that I create cracks that then limit the strength of the system. That doesn't appear to be what we see either. Okay? So he would argue that your cracks then follow you get an irregular saturation front, and that creates problems and potentials for cracking. I'm not sure that that's always the case, but it may be the case in gel type systems which are extremely high surface area where you have very little opportunity for rearrangement. Confusing. He draws the first and second falling rate period. This way, water saturates the pore structure, the pore walls, and then it works its way out and it forms a film on the surface. Then you get free evaporation from the surface. So you get flow of water along the pore structure. And when you get below a certain water content, this shuts off. That flow stops. Once that flow stops, there's no more movement of water to the surface as liquid water. Now it's all diffusion related, evaporation diffusion, and that's an extremely slow process. So if this process is working and your water is moving along the pore channels and then out to the surface, your evaporation rates will be greater. That's his argument. This one is that essentially low humidity, low humidity, and high temperature, you're going to see greater changes or differences in the water content from interior to exterior of the body. These are extreme cases, right? If I go to low humidity and high temperature, I have my greatest differential possible. Okay, that means that my moisture content on the surface will be low and the moisture content in the interior will be high. That is a recipe for failure. That's quite difficult to do. Okay. If I'm in low temperature and low humidity, then to look at the water content, right, draw a line here at a given time, look at it this way, okay, we have basically a very narrow difference in moisture content from interior to exterior, okay, and it says below this line shrinkage ceases. You have very little amount of shrinkage necessary still in the system, whereas here, this one in particular, you have a huge difference, and that leads to differential stresses. This is all predicated on the idea, though, that you can create cracking and drying. Okay, so I'm only going to show you this. No, I'm not. I will draw it this way. Nope, I'm not going to do it at all. So that's on ionic strength. I want to talk about sintering very briefly before we head out of here. Okay, what's the takeaway from drying? Number one. Yep, typically doesn't cause cracking, right? Number two. So you can debate on one or two. Micromechanical and macromechanical models don't seem to predict what's going on, right? If they worked, then you could use a psychometric chart. You could figure out how fast you can evaporate water to dry a system based on the mechanics of the body. To the best of my knowledge, no one does that. How do you set up drying curves? So recognizing that drying costs money and time, you're going to try to set up the most efficient drying curve that you can. Shortest time for drying, least amount of energy ideally. Okay, how long does that take? Okay, and what you'll do is you'll do experimentally. Can I dry this with this humidity level and this temperature? And if not, what do I do? Okay, ionic strength helps. That's the other thing. but we still go back to most of our problems in drying have to do with forming processes. Okay, good? So I don't mean to be rushing, but sintering densification falls into three very general categories. Solid state sintering, which was first argued to be the case, really nice work on sintering of metals. Okay, what's great about metals is you can get extremely pure metals, so you have no impurities in the system to speak of. A lot of the early work on sintering was done with metals with metal powders. Okay, they call it solid state sintering, and what that implies is there's no liquid phase in the system. And that's good. We're happy with that. Okay, that makes sense. Okay, now if I get small amounts of impurities, then I get a liquid phase in the system, and then that liquid phase facilitates the sintering process. It is my opinion that everything we see in ceramics is very likely liquid phase sintered. Okay, everything. Well, now we have a bit of a disconnect. Then you have viscous phase sintering, where you form a lot of liquid. Traditional ceramics are viscous phase sintered. Okay, porcelains, earthenwares, stoneware bodies, you form. Our calculations, our measurements show 55% liquid in the system at the densification point. So you're more than 50% liquid in the system. That's viscous phase sintering. Okay, if you're liquid phase sintering, you might be 3% liquid. Okay, and then you have to start dealing with the phase diagrams, which we can do. Okay, so there are three stages of sintering. Do you know what they are? Have you talked about sintering and thermal? Yes? Just now, this is perfect. What are your three stages of sintering? Yeah, we're really original on those, right? Initial, intermediate, and final. And then some clown introduced this idea of adhesion. I don't like it, but it's in here for completeness. Yeah, the particles stick together for some reason that we're not going to discuss, other than van der Waals forces, residual dissolved salts, blah, blah, blah. Initial, intermediate, and final. These are dictated really by the porosity in the body of the densification level. Okay, initial stage sintering, very low densification, very high porosity in the body. Okay, but you lose a lot of surface area in the initial stages of sintering. Okay, you form necks in the system. Okay, neck growth, and then densification is small at first, and then if we get into intermediate stage, we start to form pore channels. Okay, we see grain sizes increase and pore sizes increase also, and you eliminate almost all of the open porosity by the end of initial stage. In fact, you would argue that all open porosity is eliminated by the end of the intermediate stage, and then at that point you have closed off the pores. And this level, this transition from intermediate to final, occurs around 88 to 90%, okay, of the density of the body. Okay, so when you're at 88% density above that level, we consider the closed to be pores and no longer continuous and connected to the outside. Where does that 88% come from? 88% comes from what's called a percolation threshold. Particles in suspension at 12 volume percent will form a continuous network through the suspension. Okay, we call that a percolation threshold, and by comparison, when the pore structures, the pore values are less than 12%, we consider them to be no longer continuously connected. Okay, the pores change shape. The whole thing, driving force for sintering, okay, reduction of curvature. You could equate that argument to surface area. The more surface area you have, the greater the driving force for sintering and densification. Okay, so what we have is you have a surface energy term, gamma SV. So you have a free surface, you have a vapor out here, you have a solid here, and it's that surface energy. What you're doing is you are exchanging that surface energy, reducing it by converting it to gamma SS. I assume you heard about this in thermal. Well, that's good. So your solid-solid interfacial area is typically lower than your solid vapor interfacial area. And thus, there is a driving force to reduce the energy by forming solid-solid interfacial area, grain boundaries, instead of having that solid in contact with the vapor. Okay, and that is by and large everything you need to know about sintering. If you increase the surface area, you increase surface energy. Then it's a greater driving force to reduce that surface energy by doing a couple things. One could be coarsening. Okay, so in the initial stage of sintering, by the way, this is an argument for free energy. You could argue, though, that this is actually an argument for grain growth rather than an argument for sintering. So we differentiate sintering into sintering and densification. What's the difference? Any process which changes the morphology of the grain or changes the grain boundary is sintering. Processes that reduce porosity are densification. So we differentiate that way. Coarsening is usually a solid state sintering problem. Okay, coarsening could occur without densification, and what we found fascinating result recently is that the surface area reduction associated with sintering appears to be independent of the densification process. So if I create bodies that are flocculated or dispersed, I get different densities in those bodies at a different temperature, but my measured surface areas are essentially indistinguishable. So we are really interested in this phenomena right now for a concept called two-step sintering. And I will only touch on it. I don't have any slides yet because we're still generating data. What you do is you actually have a very interesting sintering curve. It looks like this. Time, temperature. You go up, you spike, you come down, you hold. Okay, and you actually dramatically reduce the grain growth potential in the system. You get full densification. This density at this point is 75 to 90% dense. Okay, and then here, this temperature might be very low. For alumina, typically we sinter around 1550 to 1600, 1500 to 1600. You might be doing this second stage someplace around 1150 or 1200. Dan D'Elia is working on this at the moment. We're generating some really interesting data. Coarsening is highly temperature dependent. Higher temperature, greater reduction in surface area. This data, ignore the shrinkage data here. This is your surface area. This is normalized. I'm not sure why they're using the natural log. We still debate on that. Delta S over S, 0, and then this is 1 over temperature on the x-axis, basically. And we're looking at what that reduction in surface area is. We took this data and converted it to other data we're looking at, and they match. It's quite interesting. He didn't do it quite with his natural log of delta S over S. Core packing is the coarsening, not necessarily true. We find in sintering and ceramic systems is that the domains will sinter first. So this whole idea of slip casting, right, and domain generation means that you will typically, in a slip cast sample, end up with a potentially larger grain size than you might predict, okay, because those domains will sinter first, and then that remaining porosity between those domains, okay, will be eliminated. But that domain, once it sinters and densifies, now it is free to grow grains, okay? And Sarah Whitke has been generating really marvelous data on the kinetics of grain growth associated with densification. And what she finds is that once, let's plot it this way, actually she does it versus log of time, which works also. She has two slopes like this. Not really a great big change. And she has other data. Shows if you do something like this. Okay. This might be 1500. This might be 1550. Okay. When densification occurs, the grain growth is the same. Okay, but the slopes of these lines are similar, but they occur. This is the point where densification occurs. So once the system densifies, grain growth is free to take off. Otherwise, what happens is the pores stop that grain growth. Okay, so let's do this. Let's look at solid state first. Okay, so typical sintering temperature is 0.8 of T sub m. What's T sub m?
That's the temperature of melting.
Melting point, and it's a capital T means it's absolute temperature. Okay, that's a rule of thumb. And that rule of thumb was developed somewhere in the 50s. I don't believe that rule of thumb is still valid because improved processing means we eliminate the large defects in the pores and we can densify at a lower temperature. Okay, Okay, and we see that over and over. Plus, as we drive down particle size and drive up surface area, the densification improves at lower temperatures. Okay, so there are a lot of really sophisticated models. Most of them came out of powder metallurgy. A lot more work being done in ceramics now and sintering in the past 25 years. Okay, solid state sintering used to be argued for alumina. We find that typically is only the case in really high purity alumina. Everything else forms a liquid in the earliest stages of sintering because of reaction of impurities with the surface of the particle. So if you think about it a little bit differently, all of your impurities in the system end up on the surface of the particles and end up in the grain boundaries when you get done. Okay? If you start thinking about it that way, it helps you understand then how those reactions will occur on the particle surface and how the sintering densification will occur. Powder metals, by the way, no problem. When you get into ceramics like alumina, small amounts of sodium. Why do I have sodium in alumina? I keep asking this question, see if I get the same response. Yeah, I make the powders with the Bayer process. Typically, right, use sodium hydroxide to dissolve aluminum hydrate or hydrated alumina within the bauxite. And when I precipitate out with sulfuric acid, I end up with a little bit of sodium behind. And then I go to great pains to clean that out, but I always have sodium in those systems for the most part. Okay. Ferroelectrics, things like lead zirconium titanates and what have you, those are also argued to sinter by solid state mechanisms. We don't think that's true. Ashby developed this really elegant model. Perfect spheres, of course. There's 6 different mechanisms. Only the mechanisms that contribute to the 2 centers of these particles moving closer together contribute to densification. Everything else is contributing to neck formation. Okay, so you have curvature here, and you have an inverted curvature here. This becomes a sink for material. So you move material from the bulk or from the exterior to that sink. Okay. Then you grow a neck. If you move material from the grain boundary, as shown here for 5 and 4, 4 is grain boundary diffusion, so it diffuses out through the grain boundary to the neck. 5 is bulk diffusion from the neck, from the grain boundary to the neck. Those contribute to densification. Those are the only 2. Everything else contributes essentially to coarsening. Okay, so material comes from the surface or comes from the bulk dislocations. Okay, then you end up with material deposits in the neck. Those do not contribute to shrinkage. Only these 2, 4 and 5, where you move material from the grain boundary. Some great pictures taken. These were nickel spheres. Okay, and you can see the necks formed. These are pretty high magnification. Okay, and then this is really early on. These are for copper, I believe. Yeah, and they show that the particles are moving, and this was done. These are 50 micron spheres. These are actually optical microscope images that may have even been drawn. Okay. So we're going to ignore the rest of that. But I'm going to show you this intermediate stage sintering. They draw these really neat drawings. But I have an image here. There we go. There. This is sintered silicon carbide. And this is one of the best examples of that intermediate stage pore forming where you get a cylindrical pore that connects basically all the pores together. Really remarkable microstructure and a difference from there. This is also obvious to have that sort of pore structure. Okay, this says 100% 1200 grit, no 240. And you can see what the structure of those pores look like. And versus, say, this, okay, where you still have a particle network, or this, where you have a particle network, okay? So this is actually a structured pore. This is what your pore channels look like. When I talked about drying, you have this regular pore channel. That's what we're talking about. Here, these are really quite uniform. This is probably my favorite down here in the lower right. Okay. So, where does that leave us? That leaves us to final stage sintering, and the argument is that curvature dictates whether a particle or a pore will grow or shrink. I like this image because you don't know what's a pore and what's a grain. It turns out it doesn't make any difference. Okay, if my curvature, so if I look at 6 here, all the curvature is flat. That means there's no movement of the grain boundary. But here, where I have a curve, okay, it says that the grain boundary wants to move in what direction? Yeah, it wants to move this way, right? So if I do that, I do this, this grain will eventually disappear. right? Or that pore will eventually disappear. So the coordination number around these particles or grains or pores dictate whether they're going to grow or shrink. Okay. Now this would argue that I have an equilibrium dihedral angle. That's this angle here, and it's 120 degrees. And if I have that equilibrium dihedral angle in an isotropic material, then the grains don't want to grow if they have 6 sides on them. If they have 7 sides, they want to grow. If they have 5 sides, they want to shrink. And there's a nice plot that predicts that. So what you have is dihedral angle. What's a dihedral angle? So this. Okay. You have material come in basically like this. And this angle like this is your dihedral angle. You can note as phi. So you would say this is a grain, this is vapor, and you can then predict what that angle would be. Okay. It's dihedral angle because there's actually 2 angles associated this way. So this and that. All right. But that angle is dictated by gamma SV and gamma SS. Okay. And that we will deal with on Friday. One more comment though. Your dihedral angle is fixed because it's dictated by the ratio of gamma SV to gamma SS. So you have a constant dihedral angle, and if on this plot you drew a horizontal line, that would tell you then, based on that dihedral angle, the pore coordination necessary for pores to shrink versus pores to grow. Okay, so as your dihedral angle goes up, okay, the coordination of the pore necessary for the pore to shrink will handle more grains around it before and while it shrinks until you get to where the pore wants to grow. Okay, so that's the argument. We'll wrap up here for today. So Thursday, 7 o'clock, correct? In here, I can order pizza for you, and that will take care of that. Okay. And then Friday, we're meeting here for the review. The exam is either Tuesday or Wednesday. Is that right? Or Wednesday or Thursday? Tuesday or Wednesday.
Yes.
I probably should write that down. Or, not and. Okay? Great. Enjoy.